Bernoulli's principle. Bernoulli's principle. Fluid flow is a complex phenomenon, but we can obtain some useful properties for steady or streamlined flows using the conservation of energy. Consider a fluid moving in a pipe of varying cross section area. Let the pipe be at varying heights. We now suppose that an incompressible fluid is flowing through a pipe in a steady flow. Its velocity must change as a consequence of equation of continuity. The force is required to produce this acceleration, which is caused by the fluid surrounding it. The pressure must be different in different regions. The Knowledge equation is a general expression that relates the pressure with difference between 2 points in a pipe to both elevation, to both velocity changes, kinetic energy change, and elevation, height changes, potential energy. The Swiss physicist Daniel Bernoulli developed this relationship in 1738. Consider the flow at two regions, one that is BC and 1 and 2. D. Consider the fluid initially lying between B and D. In an infinitesimal time interval delta T, this fluid would have moved. Suppose V1 is the speed at B and V2 at D, then fluid initially at B has moved a distance V1 delta T to C. V1 delta T is small enough to assume constant cross section across BC. In the same interval delta T, the fluid initially at D moves to E, a distance equal to V2 delta T. The pressures P1 P2 act as shown on the plane faces of area A1 and A2 binding the two regions. The work done on the fluid at the left end BC is W1 P1 A1 B1 delta T is equal to P1 delta V, and since the same volume delta V passes through both the regions from the equation of continuity, the work done by the fluid at the other end is W2 V2 A2 V2 delta T P2 delta V2 V2 delta V, or the work done on the fluid is minus P2 delta V. So work done on the fluid is VW1 minus W2 P1 P2 delta V. Part of this work goes into changing the kinetic energy of the fluid, and the part goes into changing the gravitational potential energy. If the density of the fluid is rho and delta M, rho A1 V1 delta T is equal to rho delta V is the mass passing through the pipe in time delta T, then change in gravitational potential energy delta U is equal to rho G delta V H2 minus H1. Change in its kinetic energy is delta K is half of rho delta V V2 square minus V1 square velocity square. So we can employ the work energy theorem to this volume of the fluid, and this is P1 minus P2 delta V is equal to half of rho delta V V2 square minus V1 square plus rho G delta V H2 minus H1. Means the work is used in giving the kinetic energy and the potential energy. We know divide each term by delta V to obtain P1 minus P2 is equal to this rho V2 square minus V1 square plus rho G H2 minus H1. So we can rearrange the above terms to obtain P1 half of rho V1 square plus rho G H1 plus P2 is equal to P2 plus half of rho V2 square plus rho G H2. So this is the Bernoulli equation. Since 1 and 2 refers to any two locations along the pipeline, we may write the expression in general as P plus half of rho V square plus rho GH is equal to constant. In other words, Bernoulli's relation may be stated as follows. As we move along a streamline, the sum of the pressures and the kinetic energy per unit volume rho V square by 2 and the potential energy per unit volume rho GH remains a constant. Note that in applying the energy conservation principle, there is an assumption that no energy is lost due to friction, but in fact when fluids flow some energy does get lost due to internal friction. This arises due to the fact that in a fluid flow the different layers of the fluid flow with different velocity. These layers exert frictional forces on each resulting in the loss of energy. This property of the fluid is called viscosity, and the lost kinetic energy of the fluid gets converted into heat energy. Thus Bernoulli equation ideally applies to fluids with zero viscosity or non-viscous fluids. Another restriction on application of Bernoulli theorem is that fluids must be incompressible, as the elastic energy of the fluid is not taken into consideration. In practice, at a large number of useful applications, it can help explain a wide variety of phenomena of flow, viscosity, incompressible fluids. Bernoulli's equation also does not hold for non-steady or turbulent flows, because in that situation velocity and pressure are constantly fluctuating in time. When a fluid is at rest, its velocity is zero everywhere. Bernoulli's equation becomes this: P1 minus P2 rho G H2 minus H1.